In this lecture we are going to discuss about serial in serial out shift register, 3-bit serial in serial out shift register, design coding with verilog, nothing but RTL coding in verilog, and test bench coding also in verilog. Okay, so this design coding is the functionality or concept or behavior of the serial in serial out register. And to check this design code or to verify the functionality of this design code, whether we coded this design properly or not, we write the test bench code. Okay, that also in verilog, right? So first we'll see a design or RTL code. So any verilog code, whether it is a test bench code or a RTL code, even in RTL code there can be different style, whatever the style it can be. Any code should start with the keyword module, okay, and it should end with end module. There is no space in end module and there is no semicolon at the ending. Okay, so after this module keyword, after every keyword we have to maintain space. That's compulsory. Okay, so after this module keyword I will maintain space. Then here we have to give the module name. This module name I given as serial in serial out SISO. You can give any other name, it is not fixed. Okay, there are some rules to give this module name. This module name first character, it should not start with number, but number you can use any other place. Okay, so along with the numbers you can use small letters, capital letters, underscore. Okay, so by following those rules you can give any name to this module. So here I given SISO, serial in serial out. Then after module name we have to give normal bracket, and this normal bracket has to end. At the ending we have to use semicolon. In this bracket we have to write port list or terminal list or interface list of the serial in serial out shift register. Okay, so to know the port list, the better approach is, so here I assumed this 3-bit serial in serial out shift register as a block box. Okay, one box. So here I am giving my serial input, and here I am giving my clock, and here I am giving reset, and from here I am taking output. Okay, observe this direction, clock or reset to serial in, they going inside, so there are input ports, and the serial node is coming out, so this is a output port. So I am giving input at left side, so it will become right shift register. Suppose if I give my serial in this side and output I take this side, it will become left shift register. Okay, in this case serial in also inward, clock also inward, and reset also inward. They become input ports, whether it is a right shift or left shift, and the serial out, whether it is a right shift or left shift, it will become output port. Okay, and observe when I giving, what is the data I am giving here, 001, this 1 will go first. Okay, when I giving data at left side, but see here when I giving data at right side, this whatever first bit that will go inside, whatever go inside that will come out. Okay, so here also this one going inside, that will come out first. Okay, right. So to know the port list, it's a good practice to represent whole design like a black box and name the terminal list like this with directions. Okay, so from here we understood serial in, clock or reset, and serial out are output ports. What is this Q naught I will tell. Okay, now come to the code. So here I will list clock, reset, serial in, serial out. These names we can give any names. Some people can give CLOCK, RESCT. You can give any names. Suppose whatever the names you give here, same names you have to maintain in whole coding, in RTL and test bench coding. Okay, right. And this clock or reset, serial in, serial out order, no matter, you can give in any order. Okay, the thing is you have to list all the inputs and outputs here, and they have to separate by commas. Okay, now this is the first line. Now coming to the second line. So in this port list I just included all the ports, but I have not mentioned which one are inputs and which one are outputs. So now I have to declare the ports, input ports and output ports. Okay, either you can declare input first or output later, or output later, input first. Okay, anyway you can do. So first to declare the input ports, the keyword is input, and to declare the output ports, the keyword is output. After every keyword I have to maintain space, I told. Okay, now in this port list, what are the input ports? Clock or reset and serial in. And what is the output port? Serial out. So here there are multiple ports, so you have to maintain comma, and you should not use brackets here. Okay, in the port declaration. And this line should end with semicolon. This line also should end with semicolon. Okay. Generally, in behavioral code, I am writing this design code in behavioral style. In the behavioral style, generally you observe reg for the output ports, but here there is no reg. I will tell the reason. Okay. Now coming to the fourth line. So this line is a variable declaration. This second and third line are called port declaration. This fourth line is the variable declaration. Okay. Why variable declaration? We'll see. Suppose if I see the detailed diagram of this serial in, serial out shift register, I explained in the digital concept. First you have to watch that lecture, then come to this. Here I am explaining very briefly. Okay. Suppose if it is a 3-bit register, there will be 3 D flip-flops. So here I am applying my serial in. Okay. So that serial in will go to Q2, and this Q2 will go to Q1, and this Q1 will go to serial out. Like the data is shifting. So here in the port list I have not mentioned these connections. There is no Q in the port list, right? See here, there is no port list in the, there is no Q in the port list. But without that Q connection, data cannot shift. So that's why we need that variable Q. You can name any variable. I named as Q. Okay. So that Q size is 3-bit, because I need Q0, Q1, Q2. Okay. So this is called variable declaration, right? And why I mentioned this variable as reg? Suppose if you observe this procedural block, in this procedural block there are multiple statements. Each statement left side part you can observe, that is Q. Okay, whatever we write at the left side in the procedural block, that variable should become the reg variable. Suppose here if I write serial out, then this output port may become reg. But here I have not included any serial out, that's why I am not writing reg for this output. So the point is, when we have to write reg in behavioral style, whatever the left hand side variable, for that only we have to write. Okay, right. So now initially my all flip flop outputs are zeros. I have to start with zeros now. Okay, even in concept I told, I assumed initial outputs of flip flops is zeros. So I am giving the values to this Q0, Q1, Q2. It means Q of 0, Q of 1, Q of 2. For all outputs I am giving 0. So in this line I did two things, variable declaration and initialization, both. We should do variable declaration outside the procedural block, but we can initialize values either outside the procedural block or inside the procedural block also. Okay, right. Now coming to fifth line, I told this is in what is this? This is in behavioral style. So in the behavioral style, you have to use this construct always at the rate normal bracket, and it has to end with normal bracket. There is no semicolon. Okay, this construct is compulsory in behavioral style, and in this bracket we have to write clock edges or reset. Suppose if I want to make the circuit as synchronous reset circuit, I should not include reset here. If I want to make the circuit as asynchronous reset circuit, I have to include reset also here. Okay, and that reset can be passage reset, nothing but positive reset or active high reset, and that reset can be negative reset or active low reset or negative reset. Okay, the construct for positive is passage, and the construct for negative is negate. There is no space. Okay, even for reset and clock, passage negate applicable. Okay, so in this circuit I am using positive edge clock, that's why I have to write passage clock. After this passage keyword we have to maintain space, but there is no space in the passage. Okay, so here I am not including reset because I want to make it as a synchronous reset circuit. If you don't include reset, it doesn't mean there is no reset. So in the port list you can see the reset. Reset is there, but I want to make it synchronous reset circuit. That's why I have not included reset here. Okay, right. So even sometimes not only clock reset, we can include some other variables also based on the requirement. Okay, right. We'll see that kind of codes also later. Okay. Because why I wrote clock here? Because this I want to make the circuit operation with respect to clock edge. That's why. Okay, that also with positive clock edge. Okay, so in the this always block is called a procedural block. Always procedural block. So in this procedural block I wrote different statements, multi statements. So when there are multi statements, I should use begin end, so that they will execute one by one. And this is a behavioral style code, so I should use this non-blocking symbol, non-blocking statement symbol. You can see this symbol is called non-blocking for these statements in the procedural block. Okay, so this begin started here and this end ended here. Okay, now what is the here in this procedural block, what we do, we code the functionality of the serial in, serial out, shift register. What it is functionality? First I am giving my serial input, that is going to Q2, and from Q2 the data is going to Q1, and from Q1 the data is going to Q0. Okay, this Q0 is the ultimate output, but this Q0 is not included in the port list, so that Q0 I am assigning to S0, so that I will get the output. Whatever Q0 I am getting, just that Q0 I am sending to S0, assigning to S0. That's why this line. So this Q0 is not there in the port list. So if I want to see the output, I have to assign this Q0 to some other variable, that also serial out variable. So assign is a keyword. After keyword we have to maintain space. Okay, that's why I wrote this statement. Okay, now we'll see this functionality in the diagram. See, here I am giving my serial in, that serial in going to Q2, and that Q2 is going to Q1, and this Q1 is going to Q0 here. This Q0 I will assign to S0. Okay, so same I coded here. Okay, so this is about design coding or RTL coding, verilog RTL coding in the behavior style. Okay, so why I am calling this as a design code? Design code means the design or functionality or behavior of this design I coded here. That's why this is called design code. Okay, so here we mentioned only the design, only the behavior. We are not giving any input and output. So then where we have to give input and output? When we give input and when we check the output, then only we can know this design is coded properly. So for that I have to do test bench coding. Okay, so from the test bench code I will generate my inputs and I will check my outputs. That inputs will go to design code, and from the design code I will get my output. Okay, right. So when we coding test bench, we have to include this RTL code. So for that I used backquote include compiler directive. This is a keyword construct, so we have to use space after this, and I have to, what I am including my RTL code. What is my RTL code name? File name serial in serial out. My module name and file name both I given as serial in serial out. See here, you can see what is the module name, serial in serial out. What is the file name? See here, serial in serial out .v. I saved this design code with serial in serial out file name with .v extension. Okay, now test bench code. So that same name with .v extension we have to write here, and we have to keep in double quote. Okay, right. Now coming to the second line. So this is the test bench code. Every test bench code or any verilog code should start with the module keyword and end with end module, I told. So after module we have to maintain space, and we have to give the test bench name. Any name you can give. Here as an example I given TB, but there is no port list in the test bench, so it has to end with semicolon. Why there is no port list in the test bench? Because test bench only giving inputs to the RTL design. From the RTL design only we are getting outputs. Okay, we are not giving inputs to test bench, or we are not taking output from test bench. Okay, that's why there is no port list to the test bench. Okay, and in the third and fourth line we can see reg and wire. So whatever the inputs there in the design code, these inputs, these should be reg in the test bench, and whatever the outputs, those should be wire in the test bench. Okay, so what are my inputs? Clock, reset, SI, they should be reg, and what is my output? S0, that should be wire. Okay, right, this is fixed, these two are fixed. Okay, sometimes we write to test bench code without design. In that case these may not come. There may be some other variable declaration may come, these may not come, these ports. Okay, right. Now we have to instantiate this RTL code in the test bench code. When we instantiating, this fifth line is the instantiation or integration. When we doing that, we have to write the module name of that RTL design. I given module name serial in serial out. Then maintain space and give instance name. When we instantiating, we have to write instance name. This instance name can be anything. I given for example as DUT. And after this instance we have to write normal bracket, and it has to end, and there is a semicolon. So in this bracket what I have to write? I have to write the ports either by positional connection or named connection. Here I am using positional connection. Positional connection means, so whatever the ports order I wrote here, same ports order I have to write in the that bracket. Clock, reset, serial in, serial out. Okay, so here see, clock, reset, serial in, serial out, that order I wrote. I can write with the named also. Okay, in that case you no need to follow order. In some other code I will tell how to write with the name. Okay, now after this instantiation what we have to do? So in the test bench what we have to do, if you want to check our design functionality, if you just generate inputs, okay, you cannot analyze output properly. We have to generate inputs, data inputs, and there should be a clock and there should be a reset also. So we have to generate reset and clock also, because we want to check our design with respect to clock and with respect to reset, right? So we have to generate, or we have to code reset, we have to code clock, and we have to code input generation. So when I coding clock, here I used forever construct. So this forever construct means it will run forever. So to end the simulation, I have to mention whenever I use always or forever, to end the simulation I should mention $finish. So because of this forever, I wrote $finish here. Okay, right. So how to do clock coding, we'll see. So for clock generation, for reset generation, for input generation, and for $finish, I am using separate procedural blocks. That also I am using initial procedural blocks here. Okay, why only initial I used here, and why I used only always in the design code? Those topics we'll discuss later. Okay. So here initial I wrote initial construct, then in this initial procedural block there are two statements, so multiple statements, so that's why I used begin end. Even there is single statement, you can use begin end, not compulsory, even use nothing will happen. As a good programming practice you can use. Whenever you writing any procedural block, it's good to use begin end. Okay, so initially I want to make clock generation, means you have to generate some symmetric square wave signal. I want to generate some symmetric square wave signal, clock signal. Okay, so for that initially I kept my clock value 0. Why I kept 0? You can kept 1, you can keep 1, no problem. In that case your starting half cycle of the clock will be high. If I keep 0, it will be 0. We can keep anything. Okay, and I want to invert this clock for every 5 time minutes. Every 5 time minutes. That's why I wrote here. So after this clock equal to 0, what I have to write? Forever construct. I can code this clock with always also, but when I writing initial procedural block, inside that initial I should not write always. That's why I used forever. So forever, this is the keyword, I have to maintain space, and this is the time. Why I given 5? You can give any time. For example, I given. Okay, so it means this 5 indicating half cycle duration of the clock. Half cycle duration of the clock. So this clock should invert for every 5 time minutes. For every half cycle this clock will invert. Okay, this I will show in the waveform, so that you can understand very well in the waveform. Okay, now coming to this reset generation. Here also I started initial and I wrote begin end. Okay, initially I kept I am using pause to reset. So initially I applied 1 to reset. It means initially only at the starting of the design only I reset my circuit, but after 3 time minutes I released reset, I removed the reset. Okay, right. So why I used 3 time minutes? You can use any time, that's your wish. And why initially I used 1? You can use anything. If you want to make reset, you have to make it 1, that's your wish. If you don't want to make reset, you can keep 0. That also with respect to I am telling pause to reset. Okay, right. Now input generation. Input generation means first that serial input, first I am sending 1, then after 10 time minutes I am sending 0, and after 10 time minutes I am sending one more 0. It means whatever the data I am applying, 100. 100 means here I will show. So like this, first 1 is going, then 0 is going, then 0 is going. Or you can see like this also. First 1 I am applying, then 0, then 0. Either left shift or right shift, anyway you can do this. Okay, so even in right or left shift, what is going first? 1. Okay, that's why I wrote 1 here, then 0, then 0. However you want to send the data, whatever the data you want to send, you can write accordingly. And why I use a 10 gap? For example, you can give any time, no problem. Okay, right. So then I wrote to $finish. So here I am using my simulation ending time as 50. So when you writing time anywhere, you have to use hash. See here, see here. Okay, here also time, see here also. Okay, so after this 50 un you can give semicolon, then you can write to dollar finish. Without semicolon also you can write, both will behave same, and it should end with semicolon. Okay. Right, now we'll run this code and we'll check the output. I will show the run file also. I am simulating in the model sim. So this is for library, and this is for compile, this is elaboration, this is adding the wave, and this is for simulation running. Okay, about this script how to write, I did already lectures, you can see that. Okay, now I will copy the path. I copied the path and opening my tool, model sim. Okay, I am changing the directory cd space flower brackets inside control v, enter, then do space run dot do, enter. So here I have to click no. Now I got to waveform here. Click here and zoom it to analyze properly. Okay, see, initially this is clock, this is reset, this is serial in, this is serial out. So initially I kept clock 0, that's why it is maintaining 0. After 5 time minutes I told it has to invert, that's why it inverted. And again after 5, from this is 0, this is 5, this is 5, this is 10. From here to here 5, from here to here 5. So initially 0, after 5 it inverted. From here to here again after 5 it inverted. Okay, so this is the clock generation, and you can see the simulation ending time 50. Okay, now what is the time period of this cycle? So half cycle 5, this half cycle 5, total 10. So whatever the time here we wrote in the test bench, this is giving only half cycle. If you want to know the full cycle duration time period, you have to double it. Okay, now coming to the reset analyzation. Initially I made my reset 1 after 3 time minutes, here 3 picoseconds. Okay, I will tell what is the time unit to picosecond. Okay, those things I will do in another lecture. Okay, so after 3 picoseconds I made it to 0. Okay, reset released. So later I have not applied reset anywhere. Okay, so here my intention is to tell the functionality of serial in serial out register working properly or not. Okay, I am not concentrating much on reset here, whether it is a positive reset, negative reset, or sync or async. In some other lectures I will do about reset. Okay, here whatever the serial input I am applying, that we are getting at serial out properly or not, that I want to tell, because we are verifying the design. Okay, functionality. So now serial in. So this circuit will work with respect to positive edges that we mentioned in the design code, pos edge clock. So this is the first positive edge. So at the first positive edge, what is that serial in? 1. You can see here 1. This is high 1. This is the second clock edge. What is the data here? Second bit 0. and this is third clock edge. What is the data here? 0. Okay, so I applied 1 0 0. First 1 went, then 0 went, then 0 went. This 1 went here, this 1 went, 0 went, then 0 went. Okay, so this is the third clock pulse in, serial out shift register. If it is a 3-bit register, from the third clock pulse onward we will get the output getting, it will start at third clock pulse. If it is a 4-bit register, from the fourth clock pulse we will get the output. So here we have to see the serial output at third clock pulse only, because this is a 3-bit register. What is the data in third clock pulse? This is 1. First we sent 1, that 1 should come out. Yes, 1 came. Then where is the clock pulse here? So from this is the positive edge, next positive is this one. We should get 0 na, because second bit we send 0, so 0 coming. And this is the next positive edge. Here also third bit we should get 0, so here also we are getting 0. So I send 1 0 0 and I got 1. So this one came here, this 0 came here, this 0 came here. So I sent 1 0 0 and I got 1 0 0. I sent serially and I got serially only. Okay, here this all signal representations are scalar representation. There is no bus representation or vector representation. If it is representing any bus, that will become parallel. Okay, so hence this I coded whatever design code I coded, this is working properly. Okay, right. Design completed, verification also completed, and we analyzed the output properly. Okay, right.